Everyone. Mike Richardson here. Excuse me. I'll be your instructor for about the next hour on talking about thermal imaging training programs. I'd like to start off by saying thanks to ISFSI for putting this on and giving me the opportunity to make the presentation. And thanks to everyone for taking time out of your afternoon to stop by and check it out. On the screen right now is my background and, more importantly, my contact information. I'll also make sure that information's up at the end of the presentation. But if you have any questions and I can be of assistance in any way, don't hesitate to send me an email or contact me via my cell phone. I do have the chat box up, so as we're going through, if you do have a question, feel free to type it in. If it's something I can hit pretty quick and easy, I'll probably address it as we go through the presentation. If it's possibly going to be more complicated and drawn out, I may hang on to it till we finish the presentation. I'll stick around as long as we need to this afternoon to get questions answered. So we'll try to move through the presentation here pretty quickly to stick with the schedule. And then once again, if need be, I'll stick around for as long as we need to make sure that we get our questions answered. So that being said, we'll get rolling. Our objectives, we want to take a look at, are we aware of the applicable NFPA standards on thermal imaging? Are we familiar with what needs to be included in a thermal imaging training program? And do we understand the potential consequences of not having a proper thermal imaging training program? Bottom line, unfortunately, I hate to say it, if you go out and do some research, as I've done, if you check firefighter near miss, firefighter close calls, if you read through the NIOSH line of duty death investigation reports, unfortunately, you're going to find some examples where thermal imaging has been a contributing factor to either an injury or, unfortunately, in some cases, even a line of duty death. Why is that the case? My opinion and research seems to show and support the fire service. We have an issue with our level of training we're providing to our personnel when it comes to thermal imaging. I can provide you with examples where a firefighter using a thermal imager was lost and disoriented when the thermal imager failed. They did not have any other reference point or way to find their way out of the structure. Plenty of examples where firefighters have fallen into holes or downstairs because they are relying on the camera. And we're going to talk about, and you'll see here, that may or may not obviously work all the time. I've had situations where we've had a structural collapse and no one on the scene was attempting to use a thermal imager to monitor the conditions. Also, unfortunately, an example where firefighters are using a thermal imager as pretty much their sole means of identifying a flashover. And as once again, we'll talk about, that may or may not obviously work as we need it to. So unfortunately, we have examples where we've had issues and problems. So our goal obviously is to fix that and stop that in the future. So thermal imaging training program, what do we need to have? What do we need to look at? First question for some folks would be, what is the NFPA standard for thermal imagers? The answer to that question would be 1801. This standard originally came out in 2010, which puts us in an interesting situation because for about 15 years, we had manufacturers that were making cameras to no standard. Likewise, as the fire service, we had to deal with cameras with no standard. The good news is the standard has been out. The bad news is we still have a lot of cameras that do not comply with the standard. Good question to ask yourself in your department, do you have NFPA compliant cameras? If that's not the case, is that a change you're possibly going to make down the road? If you'll notice, the 1801 standard covers things now such as performance requirements. So we actually have cameras tested by a third party to ensure that they're working and performing as need be, whereas in the past, they were simply tested by the manufacturer and we had to take their word as to what their performance level was. Another thing that we've pushed with the standard was having what we call a basic operational format, so that if the camera is NFPA compliant and you turn it on, it will come up in a basic format, which would be grayscale with white hot. It would also have some other basic features, but it wouldn't have a lot of the other, quote, bells and whistles that we've added to cameras. You have to be careful nowadays. There's some cameras out there that have a lot of additional features that if a user turns on and someone else picks it up, you got to ask yourself, are they really going to understand what they're looking at and understand the mode or the format that the camera's in? So good news is we have a standard. Once again, the bad news is we have a lot of non-compliant cameras in service. That means we have no standards, no consistency amongst cameras. Another analogy I would throw out is if I ask anybody, I need you to hit your emergency bypass valve on your SCBA, everybody knows go for the red button or the red knob. On a thermal imaging camera, if I tell you to hit a green button, it may have one, it may not, it may be an on-off button, it may be something else. So also, as we've put multiple models of cameras in service, a lot of departments, there's no consistency from one model to the next. So definitely something to take a look at and consider going down the road with your current cameras or any future purchases you may make. Next question, what is the NFPA standard for thermal imaging training? Obviously, this is the heart of what we're talking about today with our thermal imaging training programs. The answer for that one is going to be 1408. Once again, this is quote-unquote a new standard. This has only been out since 2015. So once again, we had close to probably 18 years of thermal imaging cameras being in service with no guiding documentation on what we need to be doing for training. Once again, the good news, the standard is out now. But once again, we need to ask ourselves, is your department or is your agency in compliance or following this standard on thermal imaging training? From a broad standpoint, this standard is going to cover policies and procedures, what requirements we should have as an instructor, what are our student prerequisites, and then it'll cover the key components of the thermal imaging training program itself. The good news with both of these standards, they are free, available online from NFPA for viewing. So if you do not have these standards in your department, go to the NFPA website. You can pull them both up, view them online for free. So once again, if you have questions, you have a reference to go back to and look at. To further get into the training program standard, in Section 4, it talks about the program itself. And if you're looking for some, if you will, justification for why we need these training programs, possibly with your administration, your chief, or to get some support, the standard clearly states that you shall have a program and it shall be implemented. Once again, there should also be a written policy that outlines what your training program actually consists of. Along those lines, that policy shall address the training requirements for the types of incidents where it may be used. So once again, if we're going to use it on structural firefighting, we need to have specifics that say this is how we train with thermal imaging for structural firefighting. If we're going to add something additional, such as hazmat response, once again, we should specify that in the training program. Key here at 423 is there should be an annual review of members' competence. So it says right here in the standard on an annual basis, we should be checking the competence of our members when it comes to thermal imaging operation, application, and use. Traveling around the country, doing a lot of training with departments, the same questions I'm showing you today, I ask members, and I get a lot of blank stares and a lot of I don't knows. So once again, are our programs robust? Are we covering everything we need to cover? And are our members actually competent, and have we documented that? TI training is going to need to include practical evolutions. A lot of the training that I do, unfortunately, on the one hand, is just classroom-based. I'd like to say something's better than nothing, but bottom line is thermal imaging obviously is a very hands-on practical skill. And if our training doesn't get us to that point, we're going to be limited in how successful we're going to be. So it's very important that when we do training, we actually include the practical hands-on component, and not just in a lot of cases where maybe a manufacturer rep is going to show up, do a 15, 20-minute presentation in a classroom, and we're going to call it good. You can somewhat learn on the job, but we all know there can be consequences for doing that. So good hands-on training is a key. And then once again, documentation needs to be maintained on all these things that we've outlined above. If we get continuing on with this, this needs to be both individual and crew-based training. So we need to figure out who's going to use the camera on the crew, how it's going to be used, same time making sure each member has their own individual skill set. Once again, the standard straight out says this should all be taking place before we allow people to actually take a camera and operate. This is an issue with some departments. Are you going to do your training in your recruit class on the front end, or is this something that people are getting later on down the road? If they have the potential to use a camera, obviously it's very important that we get that training done before the camera ends up in their hands and they're in a potentially life and death situation. Another key thing here is before we put new or unfamiliar thermal imagers in place, we need to do training. Once again, with thermal imaging being around for 20 years plus years now, most departments are on their second, third, or fourth thermal imager. So the key is when we put new thermal imagers in service, are we doing an appropriate level of training to go along with it? And then once again, we need classroom and hands-on training before we let people get into an IDLH environment. So, Chapter 5 gets into the instructor requirements. Obviously, with me traveling around the country, I'm invited to a lot of departments because they realize or recognize they don't have the expertise to do the training. This is obviously can be a challenge for a lot of folks. So this is where you may need to reach out to your state resources or possibly national resources, maybe where you need to send someone to a training program, FDIC, Firehouse Expo, somewhere if need be to develop or have this expertise to be able to present this material. Because once again, if we don't have good, competent instructors, how well or how effective are our programs going to ultimately be? Chapter 6 has the student requirements in it. And in a nutshell, basically it says they need to meet the JPRs for Firefighter 1. Obviously, it's key that folks have understanding of things like fire behavior before we start putting them into thermal imaging training. So that'll get us through that. Chapter 7 gets into the actual program components. So this is the key part. If you're not going to really look at anything else, dig hard into Chapter 7 and make sure that we're hitting these key areas, which is what we're going to talk about next. We need to make sure, for example, firefighters really understand if they see a color, firefighters, if they see the color red in their mind, that means run. But I hate to say it, in some cases, that can mean they're seeing temperatures as low as 300 degrees. So do we really understand when we see something like a color on a screen, what does that actually mean to us? What is the significance? Temperature measurement. We need to make sure we understand that. We're going to talk about that next in the presentation, and hopefully after we do, people will get a much better understanding for the issues that we truly have with temperature measurement. We're going to talk about the functions and the modes of the camera. We need to understand this. Once again, my experience has shown most firefighters don't truly understand how their thermal imagers are really operating. If your camera has advanced features, wireless video transmission, video recording, other things on a camera, do they actually know how to use it? And once again, this is important. I found a department that did not realize that every time they turned on their thermal imager, it was actually recording video. Had no clue it had that feature and had no clue that that was going on. Obviously, that could be a great tool because it could be downloaded for training purposes. But that could also be a huge legal liability because bottom line is whatever the camera sees, it's being recorded. So those are the kind of things we need to be aware of and take a look at. And then a very key one here is if your thermal imager fails, we have to be able to continue whatever it is we're doing. And this obviously becomes very important. Once again, we shouldn't be navigating with the camera so that if it fails, we can't get ourselves back out. We shouldn't become so reliant on it, once again, that if it fails, we can't continue whatever our assignment is on the fire ground. So that covers those parts of the program. And then the final part in 7 is it talks about the different ways to utilize the camera. So we're going to get into things such as depth perception. We're going to get into things such as reflections and so on. All these components here we're going to hit in our presentation coming up shortly. So that is pretty much NFPA 1408 in a nutshell. Once again, it's available online at the NFPA website. So you can go in, take a look at that, make some detailed notes, and then ask yourself, the program that we have, is it hitting all these components and are we doing everything that we actually need to do to get our personnel up to speed and trained properly? Because once again, based on what I'm seeing, the answer typically is that's not the case and it's not happening. So next section we'll get into will be thermal imaging technology and principles. I wanted to get into this to kind of give you some of the meat and potatoes as what should actually be in a training program, and also too to kind of show the importance of why we need to hit on these different topics and subjects. A lot of firefighters, thermal imaging training consisted of stick the battery in here, hit this button to turn it on, white's hot, black's cold, you're good, go forth and use it. Really, after this, hopefully everyone will understand and see there's a whole lot more to it that we need to be hitting. So We need to make sure that we cover the technology as well as thermal imaging principles. Once again, those are both clearly outlined in 1408. And once again, it clearly takes both to truly to succeed here and to understand that. So question number 3, what type of detector technology does your thermal imager utilize? Once again, because we're looking at 15 to 20 years in some agencies with thermal imaging, we've had multiple types of technology in use. So it's very important to know, have you switched from one technology to another? Because if that's the case, they don't always operate the same. So if we have gone from one technology to another, we need to first recognize that change has occurred and we've done updated training. The other thing we need to understand is the pros and cons or strengths and weaknesses of each technology. Which type of technology you have, obviously you'll do your homework and do your research and figure out. The ferroelectric BST, which stands for barium strontium titanate, it's the detector technology. That was the original cameras that came out, the large format cameras. This once again, 15, 20 years ago. They have stopped making those cameras and we have now switched over to microbolometer technology. If you have a newer camera, it's been made in the last 10 years, give or take, plus or minus, more than likely it's going to be a microbolometer camera. Now, once again, both technologies are still out there and in use. Prime example, my agency still uses both technologies. But nowadays, what you're going to actually find available will be microbolometer. These are the BST units that were produced. So if you've used one of these or if you have one of these, this is a BST-based thermal imager. If you don't see your thermal imager here, then it's going to be a microbolometer-based unit. But once again, contact your manufacturer, check your owner's manual, figure out which technology that you actually have. Question 4, what size detector does your thermal imager utilize? The detector, the focal plane array, the part of the camera that senses the infrared energy and then converts that into an image, that detector can come in multiple sizes. You can see here we've got 80 by 60, 160 by 120, and 320 by 240. Once again, it's important to know which one we have in our cameras, and we'll get in a little bit more as to why. All the original BST units had a 320 by 240. If we do the math, that gives us 76,800 pixels. Obviously, when we think of pixels, we think of things like TVs, video cameras, and we know the higher the pixel count, the better the image quality. Well, for us in the fire service, we told the manufacturers we wanted smaller and more economical cameras. One of the ways they achieved that was to use smaller detectors or smaller focal plane arrays, so that we have now seen a 160 by 120 and an 80 by 60 being offered. But you can see the consequence of that is our pixel count has dropped significantly. In the case of an 80 by 60, we went from 76,000 pixels down to only 4,800 pixels. Obviously, that's a huge issue with image quality. So the key here is to know what size detector you have and what you can expect from it. Doesn't mean that an 80 by 60 won't work or isn't a good camera, but it is going to have some limitations and drawbacks that you need to be aware of. There are other sizes that are now coming out because individuals like the military are actually moving in the other direction with larger focal planes. So we're getting some of their technology. So we now have some options such as a 384 by 288, which is obviously even more pixels. So you need to be aware of what type and what size detector you have and what you can expect from that. Here's just an example with the BST and then the 2 microbolometer technologies. We have VOX or vanadium oxide technology and ASI or amorphous silicon technology. Wouldn't really worry a whole lot about one or the other than knowing they're a little bit different. They may look a little different, work a little different. Typically, the vanadium oxide will be your higher end, larger detectors. Your amorphous silicon, in some cases, will be your smaller, lower end detectors. You can clearly see here that the 3 different types of technology are producing 3 different types of images. I try to stress the firefighters, don't get hung up on which one is better. Try to get hung up on knowing what you have and what it will or will not tell you. You can see here all 3 cameras will show you, hey, there's a fire towards the left corner of this room. However, you'll notice that amorphous silicon detector, which is an 80 by 60, is struggling with showing you other details, such as the window locations or the details away from the fire. So once again, it's key to know what detector you have, the technology, what size focal plane you have, and what that is or is not capable of showing you as far as use on your thermal imager. If we take a look at this video, this once again is a breakdown of the different technologies, with the microbolometers being on the left. Once again, vanadium oxide on the top and amorphosilicon on the bottom, and then your original BST technology in the upper right. You can see at this point, all three cameras are showing you the heat from the fire, but you'll notice actually the BST does a great job at showing you the convected energy and that the flow is coming from the right. You'll see the others show it, but it's a little more difficult to identify direction and flow. You'll notice that the vanadium oxide and the BST will actually identify numbers that are on the wall, whereas you'll notice the amorphosilicon lacks the detail and ability to do that. Could that matter? If you're in a building looking for a room number, this technology could be the difference in finding it, whereas this technology obviously is not going to have that capability. So once again, know what kind of technology you have and know what the pros and cons, capabilities, and limitations are of it. So please make sure you know, once again, the type of technology you have, if you've used one or the other, what's similar and what is different, and what changes or adaptations do you need to make if you change from one technology to the other. They are similar, but they are not the same. And that was a review in a nutshell. There's obviously a lot more to it, but the time we have, that's the best I can do for now. But more research, more homework to do there for you. Test question 5. How many gain sensitivity modes does your thermal imager have? This is very key on how we're going to use and operate. Your original BST cameras more or less had a single mode. Some of the cameras you could manually control the sensitivity, but they pretty much operated in a single mode. Your microbolometer technology nowadays typically is going to be a 2 or 3 mode camera. Now, check, because there are some newer microbolometers coming out that are smaller in size and cost, and one of the ways they may be saving money and making that work is using a single mode. So once again, refer to your manufacturer's guidelines, your directions, your owner manual, and determine how many modes your camera has. Most cameras are going to have 2 modes. So if we take a look here, we'll see that in operation. This is the high sensitivity mode. It's going to stay in that mode until it sees too much energy and saturates. It's then going to go into a low sensitivity mode. So once again, most cameras will start in a high sensitivity mode. This is going to be looking for energy once the camera starts to saturate, so your screen goes white or red for a significant portion. It's going to need to shift its sensitivity. If not, your entire screen would saturate. So this is what you would see in a 2-mode camera. This particular one is an MSA, but you would also see similar things with a Bullard and others. 2-mode cameras are the most common one that you're going to run into. This next example is a 3-mode camera. This particular one is an ISG. You will see the high sensitivity, medium, and then low sensitivity. Now, if you've noticed, your on-screen symbology doesn't say L right now. Once again, this was all done before a standard was developed. So a key thing for you to know is how many modes does your camera have, and how can you identify which mode it is actually in. Because once again, non-compliant cameras, there is no standard for the symbology. Also be aware, there are some cameras out there that when they shift modes, they have no on-screen indicator to tell you that they are doing it. So you're going to have to become a good enough operator to know, looking at your image quality, what particular mode you are in. So the next question I usually get is, what's the significance? Why is it important to know about these modes? So I'll give you an example here where you're going to see a 3-mode camera, high, medium, and then you'll see here low sensitivity. So you can see the camera's having adjust based on the amount of heat or energy that's coming into the field of view. So once again, that was a 3-mode camera. I'm going to play the video again, and I want you to look and see if you can identify something that's very important. So once again, take a look at the image and see if you're able to identify what we need to be able to see as firefighters. Going to now show you those 3 modes in that image. If you look very carefully, if you had a chance to see it, you would notice that actually right here we have a down firefighter. This is the helmet, the arms, the body, and the legs. You can see in the medium sensitivity mode, that's my best bet at identifying that. You can see in the low sensitivity mode, I cannot see anything in that corner at all. I lose that detail. Now, if you only have a 2-mode camera, your best bet would be your low mode. Since this is a 3-mode camera, medium is my best bet. But typically with the camera, you're going to want that high sensitivity to get that detail. So as operators, it's important we understand this. By nature, most firefighters want to point a camera at the heat source, at the fire, in the direction of the fire. The consequence of doing that is your camera will typically go into a low sensitivity mode. Doing so, as you can see, will drastically reduce your ability to identify details in the background because the camera is basically trying to optimize itself for the heat source. Reality is, we need to know where the fire and heat's at, but if I need to find a door or window for egress, I'm going to have a hard time seeing it. If I'm looking for victims, once again, they're going to blend into the background. So once again, it's key that we know modes, what that impacts, and how that affects our operations. Next thing is, can we control these modes? Some cameras will allow us to do that, some will not. Once again, you need to know, how does your thermal imager operate? Most cameras, the modes are automated, but newer cameras that are coming out, some of them will give you the option to control the modes. The key is to make sure we're in the right mode for whatever it is we're doing. If not, then we could have a useless camera. Some cameras have additional modes, not just sensitivity or gain modes, but what we would call operational modes. This is a newer camera here that actually has 5 modes. If we'll take a look here, this is one of those modes. This is a thermal scan mode. By going into this menu, I can tell this camera, in this case, anything that's above 90 degrees, I want you to color it yellow or orange. So we do have camera features on cameras. Bullard has a thermal throttle. You can see FLIR. Their cameras will have modes or menus or options. Drager's cameras have modes or menus and options. So once again, we as operators need to know how to use these. As an example, this fire mode would lock your camera into low sensitivity. Once again, if I'm doing search and rescue, I do not want my thermal imager in low sensitivity. It's going to struggle with low energy details that I'm looking for. I could lock it into search and rescue mode, which will lock it into high sensitivity. However, I have to be aware as I get into heat and energy, there is a potential that that camera could saturate on me. So once again, we need to understand, does our camera have modes, either sensitivity modes or operational modes? What are they and how do we utilize them effectively? Once again, if not, we're not using our camera to its fullest potential, and or we may even be doing something that could be dangerous, putting a camera into a mode that's going to actually make it ineffective. Question came up, is the sensitivity the same as the thermal throttle as a Bullard T3? Once again, the Bullard T3, the thermal throttle is an additional feature. And what it's going to do is it's going to allow you to color things based on the point that you set on the camera. So it's not so much controlling the overall sensitivity of the camera, but it is controlling at what point the camera will turn something a color. In that case, it's the color blue. So that's kind of an operational mode or an additional feature. Okay. Hopefully everybody's good on modes now and understands the importance of that. Once again, we need to use them properly or we're going to run into problems. Okay. Next thing real quick is temperature measurement. And as I mentioned earlier, we need to make sure we truly understand its capabilities and its limitations. Once again, I've seen in a lot of cases where firefighters are really misusing this feature. We even have fire service instructors who are telling them to use this feature in ways that they really should not be doing. So we need to make sure we're clear on temperature measurement. There's a lot of things that affect temperature measurement. I went through an 80-hour training program to fully understand the ins and outs of temperature measurement. Obviously, most firefighters are not getting that degree of training. Also, our cameras don't have the capability to address all these issues. So the primary issues that we want to look at on question 7, we need to consider something called distance to spot ratio. We need to consider how it works and remember what it's going to actually measure, and then also be aware of reflections and reflected energy. So if we take a look at these, Key here is, once again, there are other factors. There's things such as emissivity. So there are other things that come into play, but for the time we have today, I'm going to focus on these three because, in my opinion, they're the most common issues we run into and some of the most important ones. So starting off with distance to spot ratio. Your camera is not a laser beam. It doesn't use a laser to measure temperature. It doesn't go out in a single point. If your camera has a laser pointer on it, that's strictly to show you the direction it's pointed. It has nothing to do with actual temperature measurement. The problem with the thermal imager is the area that it's measuring temperature in is conical in shape. It's a cone, similar to a flashlight light beam. The farther back we get, the bigger the cone gets. The closer we get to what we're trying to measure, the smaller the cone gets. The problem we run into is our cone, everything inside of our cone gets averaged together. So if I put my crosshairs or whatever I have in my camera on object Y to try to get a temperature, the problem is my cone is also encompassing the background. It's going to actually average those two together. What kind of problems can that cause? Here's an example. We see a white object, so we would like to know how hot it is. We place our crosshairs on that object and we see it showing 70-some degrees. At that point, most of us would probably say, no worry, we don't need to check it. The reality is, even though the crosshairs on the object, the area being measured is significantly larger. So we're actually averaging that object with the cooler background around it. You'll notice as we get closer, the area that we're measuring is getting smaller and smaller. You'll notice, too, our temperature's going up drastically as we're doing this. If we continued, you would see that at 30 feet, we had our original 70-degree measurement. By the time we made it to 5 feet, we actually were up to 325. That's because at 5 feet, we're measuring only the hottest part of that object, and we're not averaging in a much cooler background. So it's very important that you understand with your thermal imager what your distance to spot ratio is. In other words, how close do you need to be to a given object in order to get an accurate temperature reading? If it's a small object, in many cases, as you can see, you're going to have to be very, very close to get an accurate reading. If it's a much larger object, obviously there's more room for error, more room for that cone to measure. You probably will get away with it. But this is something you can do in the firehouse, pick a hot object, space heater, in this case an iron like you iron your clothes with. See how close you have to get before your temperature reading actually stabilizes. Another thing we need to remember on temperature measurement is that temperature measurement really works effectively on surfaces. It does not work effectively on things like air and gases or flames. I've had a lot of scenarios where people tell me they're shooting the temperature at the ceiling level to figure out how hot the environment is they're in. The key you have to remember is the reading you're going to get will realistically probably be the actual temperature of a surface. So in that case, the surface of the ceiling. As far as flames go, to give you an example of what I'm talking about, we have a propane torch, which I think most of us would agree is significantly hot. We're going to place our crosshairs on it. We're going to see that we only get 107, 114 degrees. Once again, you can see the camera cannot fully register the temperature of that flame because it's not really there. Now, if we took that flame and placed it up against a surface, like a wall or something, we would probably register more of that heat energy because, once again, it can register heat on surfaces or temperature on surfaces. But as you can see, it's going to struggle with anything that's strictly in a gaseous, a vapor, or an air state because truly it's not there. Now, as we add more things to air, in the case of firefighting smoke, when we get really, really heavy particulate matter in smoke, we may start to register some of that temperature. However, it's going to be inconsistent and inaccurate as to what the actual temperature is. So once again, we need to be very cautious relying on temperature measurement because, as you can see, there's a huge room for error there. If we take a look at another one is reflection. A lot of people said a way to identify as a reflection is put your temperature measurement on it. A reflection can't have a temperature. Actually, that's not true. You'll see here we have one actual flame in reality, but I'm getting a reflection of that flame on the backsplash. If you'll notice, my temperature measurement feature does not change in temperature as I go from the actual flame to the reflection. In other words, the camera cannot tell the difference. If you also notice, my temperature measurement never went above 300 degrees. Obviously, once again, that flame is significantly hotter than 300 degrees, but that camera can only register the energy in that case that's really being absorbed or reflected off of the surfaces that it's seeing. So once again, please be very careful with your temperature measurement. How accurate is it? In some cases, it could possibly be plus or minus a couple degrees, but I've obviously shown you examples where it was plus or minus a couple hundred degrees. So there's a huge potential for error with temperature measurement. Please make sure we really understand it and we're up to speed with it. If not, we're going to have firefighters using it improperly, potentially getting injured or killed because they believe it's much cooler or believe it's much cooler than what it actually is. Next, so once again, please take it home. No solid surfaces, no flames and gases, and no the issue with distance to spot. Next thing we'll get into is our color options. What do you have, and once again, what does it mean? We had no standard for years, so unfortunately there is no consistency in the fire service. Red could be 300 degrees or red could be 2,000 degrees. So once again, we need to know, does red mean, hey, this is a major hazard, we need to evacuate, we need to change what we're doing? Or is red simply an indicator that, hey, we need to pay attention to this, put water on it, we're good? You're going to have to do your homework and refer to your manufacturer's guidelines because that's the only way you're going to know the answers to these questions. So once again, what will the actual temperature be? It could be any temperature based on who makes your thermal imager. Give you some examples. Once again, temperature can also be related to mode. This is a 2-mode camera. So in the initial high sensitivity mode, I had a reading that red was 500. You'll see when it shifts into the low sensitivity mode that it's now coloring red at 1200. So on this particular camera, red could be 500 or red could be 1200. So once again, you have to know your thermal imager. Some cameras will only color in one mode. Some cameras will color in both modes. Some cameras will color at the same temperature point. Some cameras will color at multiple temperature points. So you really need to do your homework and look at what you have in your thermal imager. This is a 3-mode camera, red at 200, red at 450, and finally red at 2000. So once again, red could mean, hey, just pay attention to that, or red in the case of 2000 degrees probably means we shouldn't be here, we need to be getting out. So once again, you have to understand the exact specifications for your camera and what colors are going to equate to what temperatures. And be very cautious that when you see a color and look back and it's gone away, make sure you don't mistake that for something getting cooler. Going back to this video, I have a lot of red initially. If I looked away from the camera while it shifted modes and looked back, I could mistake this lack of red now for getting cooler. Didn't actually get cooler, it actually got hot enough to cause it to shift modes. So the key there, once again, is we've got to understand how these features are actually operating. So once again, know your colorization points and what that means to you. Is your thermal imager equipped with reverse polarity? Yes or no? A lot of people would say, obviously, what the heck is reverse polarity before I can answer this question? We normally use a camera where white is hot. But believe it or not, we now have thermal imagers in the fire service where black can be hot. This was something that was taken from the military. It makes sense for certain applications. But obviously in firefighting, this would be the complete opposite of what most people expect. So we have to be very, very careful. If your camera has reverse polarity, you understand what it is and whether it is on or it is off. Because if I obviously gave someone a camera who's used to white hot, they're not aware it's in reverse polarity, now it's black is hot, they're going to be completely backwards in their decision-making process. It's also important to note, some thermal imaging cameras can malfunction in reverse polarity unintentionally. So something that we do anytime we turn on a thermal imager, we will point it at a fellow crew member. In most cases, any normal situation we're going to be in, a face should turn white compared to a background because typically we're warmer than the background in most settings. If you look at someone's face and it's solid black, ask yourself, is their face really cooler than the background you're in? If it's not, then you need to be aware your camera may have reversed polarity unintentionally. So once again, this could be a feature you find on the camera, or this could be something that inadvertently happens to a camera and malfunction. But we need to know what it is and how to recognize it and identify it. Next thing we'll get into is the actual principles. So we finished up with technology. Now we'll actually get into thermal imaging principles. What forms of heat and energy can we see with our cameras? We can actually see conduction, convection, and radiation. It's very important for us to understand this because we need to understand what is the camera actually showing us. It gives us an image, but we have to interpret that image. Image interpretation is very important. If we take a look at this next video, I'll ask people, what are you seeing and what is going on? I'll ask people, is the fire in the room you're in? Is the fire above you, below you? Where exactly is it located? This is what we have to figure out. If we open the window to the outside, you'll notice it was very dark and very cold. The fire in this case is actually below us. We're seeing the heat and energy conducted into the floor assembly. If you'll notice, that energy is also being conducted through structural elements in the wall. Most people would assume with wood frame construction, you wouldn't see this. They would be correct. This is not a wood frame building, it's a metal frame building. Metal is obviously a very good conductor. That's why I'm actually seeing the heat and energy transferred into the floor and up through the structural elements. So it's very important we understand heat energy principles, but also we can tie that into the building construction that we're operating in. Once again, we can't use one without the other. Which materials can produce a reflection? The answer is anything shiny. We need to be very careful when it comes to reflections because this could trick us or fool us. So if we take a look in this video, we can see a window, a door, 2 additional doors, and another window. Obviously, I'm keeping track of this because if I need an egress route, I need to know where to go to. So in the center, I have 2 doors. Reality is, how many doors do we have in the center? We actually only have 1. Our second door is a reflection off of the wall that kicks out. This is actually just a piece of aluminized insulation. What I'm now going to do is come directly in line with that and wave. Lo and behold, someone's waving back. I'm seeing myself in a reflection. It's very important we know how to recognize reflections as they can seriously throw us off. We could identify a door or window that we try to get to for egress that's not really there. We could go to the bottom of the stairs looking for the fire, see the fire to the left and go left, not realizing we're going towards the reflection of the fire, not the fire itself. So we need to train and work and make sure we understand what can produce reflections, how we can possibly identify those and avoid them so that we're not being tricked or fooled into doing something we really shouldn't do. What materials can infrared energy pass through? Infrared energy will not pass through water. There's one type of glass that can pass through, which is old lead glass. But anything that's new, especially double and triple pane, polycarbonate, etc., plastics, it will not pass through. Once again, to give you an example, with water, as we say, the old magic trick, now you see it, now you don't. I've seen examples where people were looking for drowning victims with cameras. I've seen examples where people were looking for victims that had fallen under a sheet of ice. Infrared energy cannot pass through water. So it's important to remember we can't see through water with a thermal imager. Plastics, this is an example of something we might find in a commercial building, a grocery store. Visible light will pass through this plastic, but infrared energy will not. So it's important to remember here, if that plastic was the same temperature as the wall, we may not be able to separate the two at all. But the key to remember, just because we can see through it with our eyes doesn't mean a thermal imager can see through it. There's a lot of things that long-wave infrared energy will not pass through. We need to make sure we know what those are so we don't make a mistake trying to identify something and miss it because we can't see through something. What color or shades will victims be in a fire? Usual answer I get, white. It's what we're very common used to seeing. Obviously, we know, though, it could be all of the above. A typical victim in a normal environment are warmer, so yes, white against a cool background. However, some things to remember. Firefighters, our gear keeps heat out, but it also keeps heat in. As a firefighter, we typically tend to absorb room temperature. So we have to be careful. We're looking for a down firefighter that we don't lose them because we don't have the temperature difference we need to identify them. And obviously, firefighter could be cooler in a much heated environment. Key thing to remember on firefighters, your SCBA cylinders should be auto-refrigerating if you're breathing air. So a good thing to look for on a firefighter is the cold cylinder. If you stop breathing air, though, and your temperature cylinders had time, or you're in a superheated environment, you may lose that distinction. Give you another example of this and what we're talking about. The hand is warmer than the environment. When the hand reaches the same temperature as the environment, it basically disappears. The hand is now cooler than the environment. So you can see in just a couple feet, in a couple seconds, something can totally change in appearance. This is what we call a thermal inversion. The temperature of the hand did not change, but the background that it's in has. And you can see how that can greatly affect our ability to identify things. So once again, it's very important to remember when we're using our camera what exactly it is we're looking for. Be careful looking for certain colors because in one environment or another, that can possibly change. Final thing here on principles is watch on your depth perception. We say don't get your head stuck in the box. We can have a lot of scenarios where we can be looking with the camera and think we have everything we need. In reality, we don't. In this case, I'm going to head for the door to get out of here. The problem is what's between me and the door. I'm going to look with the camera, and we're going to see, obviously, we can't identify the stairs. There's no difference in temperature, so those stairs do not stand out to the camera. Needless to say, if I'm not doing what I learned previously, I'm probably going to find the stairs the hard way. You'll notice in this example, I'm going to scan. Once again, now I'm going to use my tool as I should. If you can't see your feet, we need to use something to check. The tool now tells me, hey, something's there. I don't have a flat floor in front of me anymore. Knowing that now, I'll scan left and right for more detail, and now I can clearly identify the stair railing. So once again, thermal imaging is not the answer to everything. It's not the silver bullet. It's not magic. It won't solve all your problems, as we probably know. So we can't forget our basics, things like checking the floor in front of us before we walk. We can't forget to stay on reference points like a hose or a rope or an outside wall. Thermal imaging is a great tool, but it has limitations. It has cons. Hopefully now you have an idea of what some of those are, and you can make sure we're incorporating that into our training programs. Next section, the final section, will be applications. Once again, 1408 tells us we need to train on technology and theory, but we now also need to train on applying that in the real world. So we're going to take a quick look at some examples here as best I can with the time we have. So once again, to make sure we're tying this into the real world that we operate in. We could do a lot in terms of structural firefighting, size up, fire attack, search and rescue, and overhaul. The key is, are we using it every time we can to its fullest potential? Or are we failing to use it or not using it properly? From the outside, can we evaluate fire conditions? Do we want to look at windows, openings, or floor and roof lines? Of course, we know the answer would be all the above. Taking a look at windows. Remember we said infrared energy cannot pass directly through a window. But if we remember our heat and energy principles, we can clearly see that the fire will actually heat the windows through conduction. So while I can't see through the window, I can see that heat energy. Now, key once again to remember is building construction. These are old glass windows, what we saw in older construction. They show heat very rapidly. They also fail very rapidly, as we can see. Believe it or not, there's actually a third window here that you're just now starting to see. This third window is be an example of a new double or triple pane window. So you can see with enough time, 3 minutes of exposure, it is becoming visible. But you'll notice it took double the time it did with a normal glass window. Something else, though, to be aware of. Once it shows heat, they can fail very quickly. Reason being, these windows typically have gases between the panes, and those gases, once they heat, will expand and can cause a window to fail. This is an example from UL's impact of horizontal ventilation. Once again, NIST and UL have tremendous material on their website. Please take advantage of it. There's great thermal imaging training material in their materials they have on their website. So once again, looking at this, very quick on the legacy windows. The modern window does not show. It took us almost 3 to 4 minutes before the double pane or triple pane window would show, but it will ultimately show. The key when you're using the camera from outside is ask yourself, is this older building construction that will show heat quickly, or is this newer building construction that's going to mask or hide heat? Okay. Next example here we'll run into, once again, a great video from NIST. Looking without the camera, it's hard to see what I actually have other than reading smoke, but you'll see with the camera, once we get in the right position, we can clearly see, hey, we have a significant fire condition in the rear of the structure. Now my question is, do we have more? With the camera, once again, it's very evident this is actually a significant basement fire that is actually extended to the first floor. So once again, this is a great example where using the camera, I have significant information that I can use for my decision making, whereas without it, I would be forced just to read smoke. It's a great skill and we should use it as well. But another tool in the toolbox, thermal imaging, you can see would help us here. So now we're going to look from the outside and take a look at structural integrity. This is an example from UL's residential attic fire study. This is a great video, and they did multiple tests with different types of construction. Good news is they included thermal imaging footage, both from the outside and from the inside. A key that you'll note from these studies, the inside actually tends to mask and hide the heat much better than the outside. If you think about it, we have more layers and more insulation here than we do here. So if we take a look at this example, we'll see as the fire starts, we initially can identify some heat in the ridge vent and possibly in a gable here, whereas we will only have light smoke showing otherwise. You can see here we have more smoke, but we can also see with the camera very significant identification of where the fire is located and the fact that it's growing and spreading. Here you can see it's significantly intensified. Once again, here we'd be left strictly reading smoke. Now notice we have a change here. Now the question is, did conditions get better or did conditions get worse? Most people would assume less heat means conditions got better. But actually, if we take a close look, we will see the camera has actually shifted modes on us. So we went from 200-degree red to 450 red. We went from high sensitivity to medium sensitivity. Actually, my conditions are getting hotter or they are getting worse. So once again, we have to understand how our camera works and what it's telling us. A lot of people could mistake this image as something we're doing is making the situation better. In reality, the situation is getting worse. If we point our camera away from the heat, get it back into high sensitivity, we could then go back to monitoring that condition. So once again, we have to look at that and be able to monitor it. Can a thermal imager evaluate fire behavior from the interior? So we're taking a look. This is a good example of a challenge we have in thermal imaging training. This is a typical bird building where we've been doing training fires. The problem we have, the inside of this building has had a chance to saturate in terms of temperature. So you'll see when we look with the camera at this point, we don't see anything that looks significant. You have to remember, once again, the temperature in here has been significantly elevated for a period of time. If we now look from the outside, we'll see a very different story. We can clearly see that area is full of convected heat energy. Once again, you've got to understand the environment you're operating in and understand how your camera is working. If we looked for convected energy inside in this case, we saw nothing. However, if we would have looked from the outside before we entered, we would have seen that energy. So once again, this draws out the point of doing training can be challenging. We have to watch that we don't do thermal imaging training in environments where we have high heat saturation. So things like flashover containers and insulated burn buildings over a period of time, once they build up a lot of heat, they're going to mask or hide things we would see under normal conditions. So we have to be aware of this as we're putting our training programs together and how we manage that. A thermal imager may be used to predict flashover. My answer would be never, because it's a very risky procedure to be doing. However, that potential may be there. Once again, if you have the right camera and the right conditions. We can clearly identify a significant amount of convected energy here. You'll see that energy drops and that vapor layer or smoke layer drops as well. You're going to see here comes the flashover. The key to remember, actually in this situation, smoke is from ceiling to floor. You can't see your hand in front of your face. Remember, with the thermal imager, we should normally not see smoke on the camera. So when you can identify smoke or heavy layers of convected energy, that's a high hazard, high risk environment. There's enough particulate that the camera can actually see it and enough heat energy that the camera can actually see it. We know those are two ingredients that are going to potentially lead to flashover. However, you need to remember, not all cameras will see this as well as others. You also need to remember the warning time frame, as you can tell in this case, was very short. It was a matter of seconds from the time we identified it until the flashover occurred. So while I would say never try to use a camera for flashover monitoring, I would say be very careful in how you're using it and know what your camera can and can't actually do. I would definitely not use it from a temperature standpoint. As you saw in the past with the previous examples, the camera can give you some very, very low readings because it's only measuring the temperature of the surface and not the actual temperature of that gas or heat layer. From the interior, can we identify flow paths? I would say some of the time, but once again, be careful all the time. If we look in this example, we can see we clearly have a flow path that's coming from the left and it's traveling up these stairs here. So in this case, the camera was able to clearly identify the flow path. Once again, your camera, based on technology, based on environment, may or may not be able to see these convected heat currents. Once again, this is why you've got to do realistic hands-on training to know if your camera will or will not identify this. All right? So let's take this one step further. We had a flow path. Do we need to be aware of that? Absolutely. Let's watch this video again, and let's now focus on this firefighter. This firefighter is caught in the flow path, and you can see the consequence of that. If you look at all the other firefighters' gear, you can see they're very cool. If you watch once again, you'll see this firefighter's gear go from some heat to being completely saturated because they're in that convected energy pathway. This is a great opportunity where you're going to see a firefighter go from being a little bit warm to sustaining second and third degree burns in a matter of seconds. You can see here that their gear is completely saturated. With the world and environment we're operating in today, our heat release rates are off the charts. And while our gear has good thermal protection, it can only handle so much. This is why it's critical that we identify flow paths and avoid them at all costs if we can. If not, getting caught in one could result in serious injuries or burns. From the interior, can we look at structural integrity? I would look at anything and everything, but once again, remember the limitations of building construction. Once again, NIST and UL did a number of great studies looking at different types of building construction, how that's going to fail in fire as far as time limits, but they also included the thermal image. The key point that they made, once again, was the limitation of temperature measurement, okay? So key here, we've got a 1,300 degree fire in the basement, but we're only reading 70 degrees with temperature measurement. Obviously, many floor assemblies are great insulators, so they're going to mask that actual temperature that exists below. So the key here is, once again, don't rely on temperature measurement. Rely on what you can actually see with the thermal imager. Now, once again, a word of caution. Very heavy floor assembly can mask a significant amount of heat. So things like tile, terrazzo, marble, heavy floor construction could mask a high level of heat. So we have to always ask ourselves, what is the building construction and how is that going to interact with the thermal imaging camera? Here we can see some plywood flooring is showing heat at the weak points, the seams. Here we can see an OSB floor assembly showing heat very quickly. So once again, don't rely on the temperature measurement at the surface. Rely on what is the camera showing you. If we look at a real-world example here, this floor is doing a good job at masking heat. This is an old solid plank floor with hardwood and carpet. So I have multiple layers which are acting as a great insulator. However, we can see that heat is showing in other areas. So the key, once again, don't rely on your temperature measurement on the floor. Rely on what you're seeing with your camera and other indicators as to whether you may have a fire that could be compromising conditions. Once again, the floor here takes a significant amount of time before it will show heat. But if we looked in the other areas of the structure, we can clearly see heat in wall channels and vent openings and other areas to show us what we actually have going on in the structure. So once again, use your camera to its fullest potential. Don't just get reliant on temperature measurement feature. So that took care of structure fires. The final thing here, another example of an application could be hazmat response. There's a lot of things we could do with the thermal imager and hazmat response, product levels, temperature measurement, release points, etc. But we're talking about training programs here. I've seen thermal imaging training programs where someone will put up a picture of a 55-gallon drum showing a product level. Their instruction is the students is, hey, use your camera, you can identify product levels. We all know there's more to it than that. So do we have a robust program that actually shows us that? Can we use a thermal imager to identify product levels? The answer really is sometimes, not all the time. So what are those sometimes? The key here is whatever's in the container has to be able to change the outside temperature of the container. Remember, we can't see through anything with the thermal imager, but what we can do is detect changes in temperature. So remember, there are things that impact our ability to do this. They include the environment. Direct sunlight can cause problems. Also, extreme hot or cold temperatures can cause problems. Also, our container characteristics. If we have insulated containers, they're not going to show us a product level because, once again, we can't get the temperature change we need to see the product level. Also, we need to think about the product. We can't tell if a gas is in or not in a container. However, we can see possibly liquids or solids. A gas is evenly distributed unless it's compressed into a liquid. In that case, we might be able to see a product level. So when we're trying to identify it, what must we consider? Obviously, we just covered environment, container, and product. We have to look at all the above. What does this really mean? Once again, liquid product or solid product, we should see it. Container that's non-reflective and single wall, we should see a product level. Container not impacted by external heating, we should see a product level. So once again, there's a lot that goes into this. If we have a good, proper training program, we're explaining this to our students. If we simply throw a container in front of them and say, look at it, and they see a product level, we could be misleading them into thinking something's going to happen that may or may not always be the case. Once again, here's what's actually going on. A liquid or a solid product is a better conductor. Therefore, it will cool the bottom part of the container. Air, as we know, is a very poor conductor. So actually, that part of the container will tend to stay warmer. So generally, we're looking for cooler bottom, warmer top. There are possibly exceptions, though. So once again, we need to stress this to our students. So can we have false level lines? Absolutely. This is where being a good instructor and doing thorough training will pay off, because then your students will know, I'm seeing a product level versus I'm seeing a false product level. These will appear to be product levels, however, they are not. Prime example, we have an insulated rail car. It's impossible for us to see a product level. The product inside the container cannot change the outside temperature of the container. But if you look, a lot of people would mistake this as a product level because I have dark on the bottom and light on the top. If we're trained properly, we know this light on the top is due to direct sunlight heating. Therefore, I could make that call. So once again, something we need to teach people is to make comparisons. If I'm looking at containers and they're all the same color, it's very hard to say are they full or empty. But being able to compare these drums, I could say, now I can see these drums are partially full or these drums are completely full. But once again, we have to know the ins and outs, the devil's in the details. I can't compare what I'm seeing with a plastic drum with what I'm seeing with a metal drum because they have different properties and characteristics. So if we take a look here at another example, I have some tanks. The first thing I don't like about this is I have different possible materials or colors. This could cause a problem with the imager. I'm hoping my product level does not match up to that. Good news is it does not. So it appears I have a product level here. However, I have the opposite of what I should normally have. If we look, this is light where it should be dark. However, there's a good clue. The equipment that handles this product is also light, telling me this is a heated product. So the reason I have the opposite of what I would normally expect here is because I'm dealing with a heated product. Now, if I make a comparison, if this tank was full, it should be white all the way to the top. But the key question here to ask is, do these tanks hold the same product? If not, I could have a heating product here and a cooled product here. that case, this tank could be completely full. Hopefully, after seeing these examples, you'll understand the detail that you're going to have to get into in your training programs. As you can see, it takes a significant amount of material and knowledge in order to be able to train people properly on things like this. That's why we need to stress, are we really doing our job as instructors and putting good thermal imaging training programs out there? Hopefully now we've answered the questions. Are we aware of the standards? Are we familiar with what needs to be included? And do we understand the potential consequences? So once again, I would like to thank ISFSI for the opportunity, specifically CAS for supplying some of the video material. Thanks to Dan and Steve at NIST and UL for their great work in sharing it. Thanks to SafeIR and everyone there who's helping as well in putting this material together and doing training for firefighters. So thanks. I'll end the presentation at this time, but I'll be sticking around for questions.